So, welcome back friends. So, in the previous lecture we have been looking at adding potentials into the Klein-Gordon equation, because we wanted to see what we can do in non-relativistic quantum mechanics can be repeated also in relativistic quantum mechanics. Now, and we encountered something called the Klein paradox. We encountered something called the Klein paradox. The Klein paradox was giving in the strong interaction regime extremely complicated results which are unintelligible. That means these are unphysical results, okay? And that is the reason why we claim, because if we do the same procedure as we did in non-relativistic quantum mechanics in the relativistic framework, we end up having nonsensical results, and that is precisely the Klein paradox. Now, there are several lessons which we can learn. Okay. So, before that we will start revamping the entire thing essentially. So, the Klein-Gordon equation which we wrote down, okay, with interactions, we wrote it first in terms of Hamiltonian or a Lagrangian. LKG is equal to del mu phi dagger del mu phi minus m square phi dagger phi minus 1 by 4 f mu nu f mu nu. Okay. This is something called scalar QED. So, this is quantum electrodynamics, but for scalar particles. I think we have argued last week essentially in the last lectures, saying that phi represent a scalar particle, because in the non-relativistic reduction limit we will see that they are actually they do not have any spin based interactions essentially. But the interactions we added in this particular fashion are relativistic. So, this is the relativistic way we have to add the interactions essentially. Now, this how did we get del mu? Del mu is essentially nothing but p mu, okay, in the presence of the rule, okay, the rule in the presence of interactions is that del mu, the small del mu goes into something called the capital covariant derivative, sometimes called capital derivative, and this capital del mu, this is equivalent to p mu. If you want, p mu goes to p mu minus e a mu in the presence of interactions essentially. That is a basic picture we have. So, in the same way, this is the rule, the quantization interaction rule essentially. This is called minimal coupling through which interaction. In the same way, del mu becomes, this is nothing but p mu minus I e a mu. So, del mu is the capital curve del mu is nothing but the minimal coupling, or also called the covariant derivative. It is called the covariant derivative essentially. Okay. Now, one can say essentially that if I do not want completely interactions, and we derived this entire expressions essentially corresponding to this, okay, these entire expressions we wrote down in generic fashion. If you remember, we wrote down this entire thing as some del mu phi dagger del mu phi plus I e a mu del mu phi plus h c minus m square phi dagger phi plus e square a mu a mu a mu a mu phi dagger a mu should appear upstairs phi dag of phi and so on, so essentially. So from this we can we wrote the full Lagrangian, expanded it and everything, and from this one can derive the equations of motions, and this gives me the equation of motion as for the phi field as some u of x whole into phi is equal to 0, where u of x is equal to I e del mu a mu plus a mu del mu minus e square a mu a mu. Now this can be thought of as your scalar part a0 square minus a bar square. Now a mu, as you remember, a contains the scalar part and a bar, and to just make connection. So this is your Klein-Gordon equation with interaction in the full relativistic form, Gordon equation, which is the scalar electrodynamics, essentially the equation of scalar electrodynamics. This contains the free part, as you see this contains the free part and this contains the interaction part, and the interaction part which we see is del mu a mu plus hc essentially plus e square a mu plus a mu. Okay. Now just to make so okay, E square is a mu is the vector potential, now okay, a mu is the vector potential. Now what we can ask is the question essentially okay, and now I just one side remark essentially to make connection with non-relativistically what happens in Schrodinger equation, because in the non-relativistic limit we know that, change the color of the pen and the non-relativistic limit. This is nothing but 1 by del square phi, phi is the Klein-Gordon wave function, plus mu dot b plus r b plus v of phi is equal to 0. Now there are a lot of phi's here, so let us just make this as phi e, okay. V of phi e, E stands for the electrostatic essentially. So phi e is the electrostatic. So in the non-relativistic limit it is like considering this is your full dynamical part essentially, okay, and this is nothing but your static part. Electrostatic potential essentially, whereas this mu essentially is the dynamical part essentially. Now what we have considered, okay, what we have considered, okay, is that we in the Kg equations, okay, now there are several subtleties involved and everything in this case essentially, but what we have considered in the case of Kg equation when we are doing the Klein paradox is that we only consider the electrostatic potential, okay, we only consider the electrostatic potential, okay, and so instead of doing this we only considered a bar is equal to 0 and phi e not equal to 0 essentially. That is precisely what we have considered. Now this is like considering sort of but the relativistic full thing consider form is this particular fashion essentially, which has this particular fashion, but in a way we have considered it in some sort of a potential which is non-relativistic. In a way we have considered a potential which is sort of non-relativistic, essentially in the sense that only phi is considered to be non-zero, phi e, which we call as the scalar potential, which is considered to be non-zero, whereas the vector potential is set into 0 essentially. Okay. This is precisely what we considered exactly. So, what we are transforming, what we did was, when we tried to transform from non-relativistic quantum mechanics to relativistic quantum mechanics, we learnt that the potential should also be relativistic, but we ignored that. Okay. The potential should also be relativistic, okay, but we ignored that, and we considered it exactly like what we consider in a Schrodinger equation. This is the Schrodinger equation. And we considered a step potential from an electrostatic potential essentially. That is precisely what we did, okay, and that is precisely what we did, and then we considered a barrier, essentially some sort of a Coulomb barrier. So, we had so just to repeat from last time, essentially a Coulomb barrier like this. Unfortunately, this we call it as region 1, this we call it as region 2. Unfortunately, that particular thing was not saved, but anyway, with a height V0, and this we call it as region 1. Okay, this I have written it as so this we call it as region 1, this we call it as region 0, and this is the potential we have considered last time essentially. This is the potential we have considered last time. This exactly coincide with at 0 essentially. Yeah. Yeah. We call this region as Z, and then we call this as V of Z, and then this is what we did last time essentially. Now, then we did the entire analysis. We just started, we did exactly like what had, we had an incoming wave, and then we had an transmitted wave and a reflected wave essentially, and a reflected wave. This is transmitted wave, reflected wave, and then the conditions we discovered were that if the momentum here is p prime and the momentum is p, and we found 3 results in a way, 3 lessons from that essentially. 1, so the main lessons after doing all the analysis essentially, that we get nonsensical results. Okay, we got some results like okay, the first one was that R is equal to P prime plus P by P prime minus P whole square, and T is equal to minus 4 P prime minus P prime minus P P prime minus P, and then we get that T is negative. We found the transmission coefficient is negative because P prime has to be because P prime is negative, and that is the reason why we get a minus sign here, and then the transmission coefficient are greater than 1, all nonsensical results essentially. Now, the why this is happening, why these nonsensical results are coming essentially. So, the first lesson we sent was that in relativistic field theories, so if you want, these are the results we got, and then this is obviously nonsense. In the strong coupling region, we considered weak interaction limit, strong interaction limit and intermediate interaction limit, and in the strong interaction regime or potential, we find all this nonsensical guys. So, the first lesson we learned is that number 1 is positive energy states and negative energy states should not be considered separately in relativistic field theories. Relativistic quantum mechanics when we consider interactions. So, the first lesson we learned was the moment you consider interactions, the positive and negative energy states, okay, cannot be considered separately. Now, this creates the problem because in non-relativistic quantum mechanics we always consider one particle solutions essentially. So, all the solutions are only one there is no multi-particle solutions, but in relativistic quantum mechanics you have to consider multi-particle states essentially the moment you consider interactions. If you do not have interactions, which means that you do not really explain nature, okay, but if you want to explain anything in nature you have to consider interactions obviously, okay. So, the moment you do not consider interactions, you can say okay I am fine, meaning you can live separately with positive energy states and negative energy states, but the moment you consider interactions you have to consider both of them together, and this is what is imposed upon us by relativistic quantum mechanics essentially. Now, there is no other way you can get over it, and so this is important. And now what happens is, now the moment you consider interactions, if the interactions are strong enough, so if the interactions are strong enough you start producing positive energy states and negative energy. So, pair production of positive and negative energy states happens. Now, we will see how a physical picture appears. Now, right now these are just words because you do not see why they are happening, okay. If the interactions are strong enough, both positive and negative energy states come together, pair produced, and this will spoil our calculations. Now, I did not show you that this is because of the pair production that in the Klein paradox appears essentially, but it can be shown as we will see in the coming lectures essentially that the moment why this is happening is the moment you consider the wave function essentially the reason why this is happening here in this particular case is because the full potential the phi allows solutions. One can see it in a different manner that the phi allows for solutions which are both positive and negative energy. Now, as far as is free particle, it's fine essentially that you can live with only one particular solution, throw away rest of the solutions. The moment you put in interactions, what happens is the interactions contain terms which are current based essentially. See, remember that the interactions contain terms. So if you want, you can see it here, the interactions contain terms which are current. Okay, so here there is phi, okay, sorry, phi del mu phi is the interaction current. Now this is, remember, if you remember the charge current essentially, if you remember the charge current in the continuity equation of the Klein-Gordon field essentially. So this is your interaction term, this is your interaction term essentially. This interaction term can be both positive and negative, as we have seen earlier essentially, that this can be both positive and negative. So this term combines both the solutions, both positive solutions as well as negative solutions. Okay. So if you cannot throw away one solution and say I can introduce interactions essentially, there is no other, the moment you put in interactions you are combining both the solutions. Okay. You remember this is nothing but J mu essentially, which is nothing but phi dagger del mu phi minus phi del mu phi star essentially. Okay. Okay. Now this is nothing but your interaction. Okay, I can put a dagger here essentially, it's the same thing. Okay. And this combines both positive and negative energy solutions, and that is the reason why we say that if the interaction is very very strong, both these solutions are produced essentially, both these solutions are produced, and this will spoil up all our probability calculations. Okay, the probability interpretations, which are essentially nothing but your reflection and reflection coefficient and the transmission coefficients. Remember, the reflection coefficient and the transmission coefficients are nothing but the currents. Okay, the reflected current times the incident current, and the same thing with the transmitted current by the incident current essentially. Even if you take the incident current to be only made up of positive energy states essentially, the reflected current, because it is interacting with a potential, it will spoil everything essentially, because the current contains both positive and negative energy states, and that will create essentially the problems essentially, spoil our calculations. Third important lesson is that we have considered interactions to be classical essentially. The point is that the electrostatic potential is sort of classical essentially, whereas the phi's are essentially quantum mechanical. Okay. It will turn out later on essentially that the interactions also should be, to give proper interpretation, be relativistic. You cannot have something like a static potential sort of thing essentially, relativistic as well as quantum mechanical. In relativistic quantum mechanics. Which will be encompassed in something called the relativistic quantum field theory. Okay. This will be encompassed in something called the relativistic quantum field theory. So what we have seen is that this entire business of trying to do do whatever techniques we use in non-relativistic quantum mechanics, if we straightforwardly apply them in a relativistic quantum mechanical picture, this will lead to lot of problems. And in the last lecture I also mentioned that the current will be rapidly oscillating. If we consider wave functions made up of solutions, okay, if we consider wave functions of if we construct wave functions made up of solutions of the Klein-Gordon field essentially, and then smear them around some point essentially, and then these functions are completely rapidly oscillating, the current could be rapidly oscillating. And even if you consider single plane wave solutions, essentially scattering state solutions like what we have seen right now, okay, like we have considered a scattering problem, okay, we have considered a scattering problem in the Klein paradox. So, we have considered a scattering problem in the Klein paradox. What we seen, this also leads to some sort of nonsensical results, such that the moment, because this potential is considered in the relativistic framework as an interaction. This potential is considered as an interaction, and this potential in fact has the ability to create positive energy states and pair produce positive energy states and negative energy states if it is strong enough, and this will really spoil all our results. Okay. So, we have to develop new techniques, we have to develop new methods to handle this thing essentially, and these are the 3 lessons which we have considered today, essentially that you cannot consider positive and negative states separately in relativistic quantum mechanics. That means they have to be always considered together, okay, as long as you are considering interacting fields or interactions, meaning it being a potential or something essentially, okay. And if these interactions are strong enough, both positive and negative energy states considered to come together, pair produced, and they spoil our calculations. And the interactions should also be relativistic in quantum mechanical relativistic quantum field theory, okay, and quantum mechanical in relativistic quantum mechanics. We will know what this means towards the end of these lectures essentially, okay, towards the end of this thing, but this is important to keep in track that we have considered a part of the theory to be non-relativistic and a part of the theory to be relativistic. So, it is, as we will see, that there is something called it is gauge invariant, which I have introduced you a couple of lectures ago. It is gauge invariant, but not manifestly Lorentz invariant essentially. This is just a comment I am making essentially, okay, just to tell you that if you want to do relativistic quantum mechanics, we cannot use the same methods as non-relativistic quantum mechanics. So, otherwise we will end up having all these kind of problems essentially, okay. Now, we will now proceed to think of solutions. What are the kind of solutions one can think about essentially? Is this pathologically related to only the Klein-Gordon field, or are there any ways out? Okay. I will stop here and we will start with something called the Dirac theory in the next lecture.